Hi, welcome back. Now, a little while ago I made a video about this ER32 lever action collet chuck, which I made a prototype of, and there was a lot of really good feedback, and I've taken what I can of that feedback and fed it back into the model and basically brought it to essentially a complete model. I haven't built it in metal yet, but let's have a look. As you see here, it's a bit more developed than last time, so I wanted to sort of finish this concept, push this sort of through to a slightly more finalized design, and I think I've got there using some of the feedback that I was given. A lot of the feedback would have pushed the design in a different direction, or sort of basically meant a completely different concept of operation. So one of my viewers very kindly made a video explaining his thoughts on it and how it could be made better, all of which were really good ideas. However, it did change the way it would operate quite significantly. But the completed model is now available on printables. I've uploaded the Fusion file and the drawings for the core components, which are the main body, which is here, the sliding taper inside, the bearing ring, which is this yellow ring here, which the lever bearings roll on, and the lock ring in the back, which retains the Belleville washers. I don't think in the last video I told anyone what the actual washers were. They are 40mm outside diameter, 20.4 internal by 1mm thick. Now they provide around about 1,000 newtons of force, and they provide about 1mm of travel each. So I've got them stacked up opposite to each other. That's basically what we call series. That gives me 2mm of travel with the same amount of force. If you put them both the same way up and stack them, I'm not sure this really shows up on the camera, but stack them both the same way up, that puts them in parallel, and that would double the force required, so it's effectively making it twice as thick. That's the nice thing about these washers. They can be stacked or in series and parallel to give you different sort of spring rates and behaviors. The 1,000 newtons should provide a reasonable amount of clamping force. One of the comments fed back that the 130 newton meters of torque that an ER32 nut can be torqued up to, that's sort of a maximum value, would equate to about 18,000 newtons of clamping force. Now, this is 1,000 newtons of pushing force on the back of the collet, so I still don't really know how that translates to clamping force. I don't know whether it goes up or down, but 130 newton meters is a lot. This is the torque wrench that I use to do up wheel nuts on my car. It's about 2 foot long. These are the tools that I use to do up my ER32 collet chuck, and they're about 1/3 the length of the torque wrench. So there's no way I'm putting 130 newton meters of torque onto my collet chucks, and I've not had slippage issues, which I'm hoping means that when this thing gets fully built up in metal, whether it's just one of these or whether we need to double them up or get some thicker ones just for a bit more force, I think there should be enough force to do some useful work with this collet chuck. I wanted to address a few of the comments that were made because there were lots of them. So if you're interested in all the comments, just go to the old video, that's where you'll find them. But I'll just go through a few of them here that are sort of immediately pertinent to the design. So one question was sort of, why? And essentially, a lot of people have got ER collets and don't necessarily want to invest in another collet system. So I came up with this idea, sort of been brewing in my head for a long time, and it's the idea being that it's sort of small, compact, relatively easy to make, and it would mean you could you have a quick action collet chuck using existing collet system if you happen to already have ER collets. There's also a bit of an interesting problem to look at. I'm not a mechanical engineer, so even though it's a simple mechanism, it was just trying to work out how the sliding and rotating bits all would work together. A lot of people seem to like the idea of using the Belleville washers, and that was one of the driving reasons for this particular design. I've never really used them before, so just wanted to do something that used them and get a feel for how they work, what kind of forces are involved. You can read the fact that they take 1,000 newtons to compress on a data sheet, but until for me at least, until I've felt that in reality, I don't really know what it means. Someone said, why would you ever need such a thing in the home shop? You probably wouldn't. The idea behind this was, like I said, just an interesting problem that I wanted to solve. But quite often with tools, you don't know you need it until you've got it, and then you find reasons to use it. So, you know, I mean, I think that's why a lot of us have got many of the tools we have, not because we need them, but because we want them. One really valid concern was stress on the bearings of the headstock and the casting. Now, the bearings for my lathe are these large taper roller bearings. These are good for 8,000 newtons of force through them. So if there was the full 18,000 newtons of force going through these bearings, that would probably be bad. But at the moment, with the configuration I've designed, it's 1,000. I think you could easily take that up to 4,000 and not really do any damage. Remember, it's only a transient load. These are rated for 8,000 newtons of continuous load. Obviously, that does include the preload that you put on them. Another thing was that the slits in an ER collet can easily get swarf in them when you're machining things, and you'd have to clean it out every time. My solution to that is a cover, which would be made out of some, say, flexible material, 3D print or something, and that would just push over the collet nut. Make a series of them with different size holes, or you could make a hole with some slits in so it conforms to different size material. But I think that's relatively easy to keep the swarf out from that end. The other area where swarf can get in is around the bearing ring, where the slot is for the actuating arms. However, I've designed this bearing ring to cover up the entire slot, both in the open and closed positions, so that you shouldn't ever really get any dirt inside the chuck. Now, obviously, you could get dirt inside from the back direction, but as long as your spindle bore is clean and you're using the front cover, then you shouldn't ever get any swarf in the spindle bore. One really great suggestion was a set true adjustment. That's when you've got some screws around the perimeter of your back plate so that you can adjust it to run perfectly concentrically. That would be a brilliant addition to a commercial product so that you could true it to your lathe. The thinking behind this one, though, is that because you're going to be making this on your own lathe, should you choose to do so, it should be the taper in the chuck should be completely concentric to your lathe. Then it's just a case of rotating the collet in the nut when you set up to get the best concentricity you can. As the sliding taper goes in and out in a linear fashion, you should never rotate the collet, assuming when you pull the bar out for your next part, for instance, if you've just got a long bar in there, assuming you don't twist, then it should stay pretty concentric. Now, there were loads of suggestions for even better improvements, like doing an over-center mechanism, like on the We Can Do That Better video, which lots of people suggested. I have seen that. That's probably that's almost certainly a much better way of doing it, but it deviates from the initial concept. So this is, you know, a Belleville washer, spring actuated design. Maybe at some point in the future I'll do a bearing locking design. As I said, the model and the PDF drawings of the core components are on printables, so if you're really interested in those, you can go and check that out, link in the description. And thank you for watching. I will see you next time.